So these are tricky questions because even though I'm not going to ask you to draw the picture, it's still difficult because you still have to think about what that shape of that 3D region is going to look like. And that's tough because, if I'm only thinking about the x's, x is allowed to go from 0 to 2. Then if I only think about the y's, y is allowed to go from 2x up to 4. And if I only think about the z's, z is allowed to be anywhere between 0 and the square root of y squared minus 4x squared. So, while I don't have to sketch it, I do have to understand what it looks like. And so if I only think about these right now, x is 0 to 2, and then y is going to be between 2x and 4. There's 4. And there's the line y equals 2x. Okay, so that is the region in the xy plane. And the solid is going to live above this region in the xyz space, where the upper bound of this is going to have the square root of y squared minus 4x squared. And if I set z equal to the square root of y squared minus 4x squared, then I would get this z squared plus 4x squared minus y squared is equal to 0. And yeah, I think this is a cone. I think this is a cone because the points where x, y, z is equal to 0, 0, 0 is a solution to that equation, right? 4 times 0 squared minus 0 squared plus 0 squared would be 0. And so I know the origin belongs to this surface. And aside from that, like let's say this 0 was something else, like that 0 was like a 25 or something like that. And if that were the case, I would think of this more as a hyperboloid because it kind of looks like a sphere except for one of the terms is negative. And so that's a clue that it would be a hyperboloid. But this is a kind of hyperboloid where the origin is part of it. And the cone is kind of a limiting case of a hyperboloid. Let me see if I can illustrate what I'm talking about. So here we go, 3D calculator. We've got 4x squared minus y squared plus z squared is equal to, and again, normally our problem would say 0, but right, I said, like, what if I plugged in 25? Then it gives me this hyperboloid shape. And I say the cone is like a limiting case of a hyperboloid because if I scale that 25 down to, like, let's say 5, now it's starting to get skinnier around the origin. And what if instead of 5 I just had a 1? Then it's getting even skinnier. And then what if instead of 1 I had 0.01? Then it starts to neck down really close. And then if I just set this equal to 0, like, the limit here is that it turns into a cone. And so that's what I mean if I ever say the words a cone is like a limiting case of a hyperboloid. So here's my cone, and what this is saying is that this surface lives above this region in kind of a cone shape, right? And so the surface is above this. And so, okay, what we're trying to do in this problem is we're trying to rewrite using dx, dy, dz. So let me try to come up with a triple integral with bounds, or with order of integration dx, dy, dz. So the trick is saying, okay, what is my outside variable z? What would be the lowest and highest value z can take on? And since z is on the very far outside, these can be constants, right? This is the easy part. I just have to say what's the lowest constant value of z, and then what's the greatest constant value of z. And the lowest is really easy because that's given to us, right? The lowest constant value z can take is 0. The highest constant value that z can take is going to be plugging in what values of x and y would make the square root of y squared minus 4x squared the largest possible value. And so that's going to happen when x is 0, because that term is negative, and then when y is the greatest value. So like let's say y is 4 and x is 0. This would be the square root of 4 squared minus 0, so it would be 4. And so the greatest value that z can take on in this solid is the value 4. Now, whenever I think about y, the bounds on y, they could be constant, but they also might be a function of z. And so I have to think about what values y is allowed to take on as z changes. And that's kind of tough. I might start from right here and say that y is equal to the square root of 4x squared plus z squared. Because so the difficulty is that y is allowed to be a function of z, but not a function of x, right? And so this is really, really tricky to think about.
But on the minimum, we can put the x, 2x in relation to y, and on the max, we can put 4, right? Well, for the minimum, we have 2x is less than 1, right?
Right.
Can we do something with that?
No, because again, these bounds, they can't be a function of x. I don't know if this makes sense.
No, yeah, but what I'm saying is, like, can we like translate that? Or no, wait, it's not equal.
We'll have to use that for whenever we do our bounds on our x variable.
Oh.
But the order of integration means that I can make these z bounds a function of y or x, right? I can make my y bounds a function of x, but not a function of z. And then lastly, my x bounds would have to be constant because that's the last thing. That's, the last stop in the line. There's no more integrating after that. And so, again, the first variable, or the inside integral, can be a function of everything after it. And that's kind of how it works. So whenever I rewrite using this, that means my bounds on x can be a function of y and z. My bounds on y can only be a function of z, and my bounds of z can only be a constant whenever I rewrite this. And so I'm confident we got the z bounds right. I think the y bounds are going to be really difficult to think about. So y can only be a function of z, which means that I know that the upper bound on y is going to be a constant regardless of what z is, because this upper bound is always y equals 4 regardless of what that z value is. I'm trying to orient myself correctly. Okay, so if you were to draw this region in the xy plane where x is this red axis and y is this green axis, and that region we're integrating over in the xy plane is just this triangle, right? And so regardless of what the z value is, the maximum y value has to only be 4. But then the lower bound of y is going to be a function of z, because as z increases, then the lower bound of my y variable is also going to increase. And so, again, upper bound on y is going to be 4. The lower bound on y is going to be a function of z. And I'm going to get that by plugging in something for x. Right? I'm going to start from here, and I've got to plug in something for x. I'm trying to think of what I need to plug in.
Can we just okay, I'm not sure if this is right, but I still want to say it. So for the lower bound for y, it would be equal to 2x. Can we just plug in that?
No.
No, because 2x would be equivalent to y.
Because the bounds of y... wait, hold on, what you're saying. So, no, okay.
Because, I mean, if we can replace the x squared for a y and then just simplify, we'll just make it a function of z. No.
Yeah, I think you might actually be right about that.
Yeah, because then we can make a 2x equals y on that scenario.
Yeah, we can get rid of the x.
Yeah,
that's a good point. That's a good point. I think that's the direction we should go. Yeah, so what Gabriel's saying is that right here, this line is y equals 2x. So he's saying, let's just replace all of the x's with y over 2. So if I do that, go back a step. So this is 4 times y over 2 squared minus y squared plus z squared equals 0. And so 4 times y over 2 squared is just y squared.
2.
The 2 in the denominator is squared to make a 4. Yeah, okay.
Alright.
You made me think for a second. But that just gives me z equals 0. Which, okay, so I kind of get it. Because that relationship that says y equals 2x, that's the relationship between x and y when z is equal to 0 in the xy plane. And so that's not a terribly surprising result. That was a good thought, though, and I thought that was actually how we should do it. But let me think about this again. So we were going in this direction. We were saying y is equal to the square root of 4x squared plus z squared. And then...
Isn't 0 the lower bound? 0 from... Isn't it the lower bound of the y interval? Isn't it?
No, okay. So what we're saying is that the lower bound of y, and again, the y-axis is the green axis and the z-axis is the blue axis. I'm saying, how does the lower bound of y change depending on how the blue axis changes? And what I can see is that as the z value, as the blue value increases, then the lower bound on the green is also increasing, right? The top of this cone represents the lower bound on my y variable. And so I'm saying, like, what is that relationship right there? It looks like just y equals z from looking at this graph. I'm trying to think of how you would actually get that. And I think you would get that by setting x is equal to 0. Then you would just get y equals z.
The trace on the y is equal. Yeah, I would do that. Negative z to c.
So if we let z be the lower bound, and one way we can check our work is we could just evaluate both of these triple integrals, and that would be a great way of just checking to make sure we did our work correctly at the end here. But Yeah, it definitely looks to me like the lower bound on y is given by just y equals z. Okay, and then the last thing we would do is say, okay, how is x bounded by any function of y and z? Okay,
So
so my x value lower bound is going to be 0, I think, regardless of what values of y you have within the solid and regardless of what values of z you have within the solid. Regardless of y and z, your lower bound on x is always going to be 0. But the upper bound is going to be part of this cone shape, and so the upper bound has to obey some function of both y and z. And so that means I would take this and then rearrange it for x, and then rearranging this for x should give me x equals the square root of y squared minus z squared over 4. And so that, I think, is going to be my upper bound. So, if I were to give you this kind of problem on the exam, I'm not going to require you to like draw a 3D solid, but the trick is that you have to still be able to, imagine what this looks like in your head, which is really a difficult skill. Let me try to block off what this actually looks like. So, GeoGebra is a little bit tricky to use, but if I can get it to work, it could be helpful. So I should say, if z is greater than 0 and x is greater than 0, let me just try to graph the original triple integral. If z is greater than 0, x is greater than 0, that might be the trick. Then what I want to graph is z equals the square root of y squared minus 4x squared. Why did I get away with my z equals? Ugh. So maybe I can't say z. Maybe I have to say the square root of, shoot. Because GeoGebra is really difficult to use, in my opinion. I wish it were easier. I wish this were... Come on. Oh, come on, let me select stuff. Let me select, ugh. Okay, we're trying again. Here we go. If the square root, no, I'm not going to do the square root. If y squared minus 4x squared is greater than 0, and x is greater than 0, comma, z equals the square root of y squared minus 4x squared. That is almost exactly what I want. Almost. Oh gosh, not exactly though. Why did it do away with the inside of my cone here? If I get rid of the and x is greater than 0, what happens then? Okay, so that's the top half of my cone. The x greater than 0 was supposed to only get rid of this half, but instead it was getting rid of the middle part because GeoGebra is not perfect. Okay, anyways, I don't know if this is more or less clear, but the solid we were talking about is just that solid that's trapped in between these planes and this section right here, right? So you don't have to draw it, but you have to kind of know what it looks like. Anyways, let's quickly try to evaluate both this triple integral and this triple integral and see if we get the same answer. And if we get the same answer, then that's a really good sign that we did everything correctly. And so let's take the integral from 0 to 2 of the integral from 2x to 4 of the integral from 0 to square root y squared minus 4x squared of 1, and then the order was dx dy dt. Boop. So that looks like it understood me correctly. And it took too long to compute. Come on, that doesn't take that long to compute. Okay, I guess we're gonna have to do it by hand. That's really obnoxious. Okay, yeah, because how hard could it be? If it is, I don't really know how. I'm sure it is. I'm sure the answer is yes. I just I don't know how off the top of my head because I don't use MATLAB enough. Okay, so if I were going to take the antiderivative of 1 with respect to z, then it would just be a z. And then if I plug in, then it's just going to be the double integral from 0 to 2 of 2x to 4 of the square root of y squared minus 4x squared dy dx. Okay. If I take the antiderivative of that junk with respect to y, then the antiderivative would be 1 over the square root of y squared minus 4x squared times 2y. And then, am I forgetting something constant maybe? 1/2 out here? -1/2. Because it's the antiderivative power rule. Right, so you, oh no, shoot, I just took the derivative. I didn't take the antiderivative.
Yeah.
Okay. Rookie mistake. So if I were trying to take the antiderivative of all that junk, let's put that in Wolfram Alpha. Let's put that in Wolfram Alpha and just do one step and see if it will,
It'll actually solve.
and see if it'll actually solve, yeah. So we don't have to say 0 to square root of all that. We can just do, of 1, that should be there. Okay, now, man, this is just a show of weakness by Wolfram Alpha. I don't know why they can't figure this out faster.
You should have X, Y, and Z. Doesn't work through
Maybe
ChatGPT.
Wait, did I do this wrong? Okay, the order of integration should be dz, dy, dx. So I put it into Wolfram Alpha wrong. Maybe that's why we're getting that error. Yeah, okay.
Oh,
User error. So the answer we're looking for is 8.3 Oh, 8 pi over 3. 8 pi over 3 is our answer. So now let's try to do it again, but with this. And see if it works. So 0 to 4, z to 4. And then the last bound is 0 to square root y squared minus z squared. Divided by 4. And then the order of integration should be dx, dy, dz, if we did everything right. Dx, dy, dz. We're looking for what? 8 pi over 3? Ah, we did it. Okay. So that's a way to check your work if you're doing this kind of problem. You could